We've been discussing states of matter and what makes a solid behave as the way it does in a liquid and a gas. And it has to do not only with their kinetic energy, but with a certain amount of force of attraction that's holding the particles together as a solid or a liquid. And those forces are called intermolecular forces. So if we were to look at these three solids, and what they are is, this is sugar, this is ice or water, and then this is salt. And we wanted to see what kind of forces were holding them together, or how strong the forces were that were holding them together. We could start to heat them. And we want to see which one would melt the fastest. And if you melt faster than your others, that means your forces of attraction are not as strong. That's going to hold you together as a solid. So if we start out with equal amounts of each one of those three substances, after 1 minute, you see that the water, the ice, solid ice, has now turned to a liquid. So the ice has melted first. After about 2 minutes, 2.5 minutes, we look at the sugar, and the sugar has started to melt. After 3, 4, 5, 7 minutes, the salt will not melt. So the melting point tells us about a compound, how strong the forces are that hold it together as a compound. So if you have a weaker attractive force, you're going to not be able to withstand high heat. If you have a very, very strong attractive force, you will. So the difference between the melting points of salt, sugar, and ice, we could see the ice, which was made of water, melted first, followed by the sugar, and the salt's not going to melt. So what is the difference in their types of bonds? So we know that sugar has the chemical formula of C6H12O6. Salt has the chemical formula of NaCl. Water has the formula of H2O. So we were looking at chemical bonding in last semester, and we see that bonds can form one of two ways. They can be ionic or they could be covalent. If it's an ionic bond, that means you have a metal combining with a nonmetal, and we have a transfer of electrons. So here sodium is a metal, chlorine's a nonmetal. We have a transfer of electrons, and this is that ionic bond, very, very strong, holding it together. Or you could be covalent. And with covalent compounds, we see it's two nonmetals. So here we have carbon, hydrogen, oxygen. Those are all nonmetals. Here we have hydrogen and oxygen. Those are all nonmetals. So the sugar and the water are covalent, and the salt is ionic. The sugar and the water were able to be melted, but the salt was not. So even though we have an ionic versus a covalent, we still had differences in the melting times of the sugar and the water, even though they were both covalent. So since there's differences in their melting points, there must be differences in the forces that hold them together. So we're not just looking at a covalent bond, we're looking at something else. So we can form a covalent bond in one of two ways. If you remember, one of them is polar and the other is nonpolar. And when we talk about something being polar, we're talking about something having opposite ends. So polar molecules have one atom that's a little more electronegative than another, and it tends to attract the electrons to its side a little bit more. So example, if we have water, H2O, and we draw the molecule, and we know that oxygen's in group 16, has 6 valence electrons that are arranged like that, and we put our hydrogens in. I'll give the hydrogens electrons as an X. Hydrogen and oxygen are sharing that electrons. There's no ions being formed. There's no electron transfer. They're sharing. But oxygen is a little more electron greedy than hydrogen. So oxygen has a tendency to pull the electrons more towards its side than the hydrogen. So as these electrons, these bonding electrons from hydrogen, spend more time over at oxygen's house, it makes oxygen feel a little bit negative. It's not an ion, it just has a slight negative charge on that end of the molecule. And that's what this symbol means, partial. So with the electrons over at oxygen's house most of the time, that leaves each hydrogen feeling a little positive, slightly positive. So when it's polar, we say it has opposite ends. And so if you look at this molecule, on this side we have a positive kind of charged end, and on this side we have a negative, oppositely charged ends, and that's what makes it polar. If the substance is nonpolar covalent, we still have two nonmetals, but they're generally of the same type. So when we talked about those Hofbrinkel, those were the diatomic molecules, the diatomic gases. Well, these each would form a nonpolar covalent molecule. You have hydrogen bonding with itself, oxygen bonding with itself. So the difference in electronegativity, there isn't going to be one. So if we have one hydrogen with its one electron and it forms a bond with another hydrogen with its one electron, neither one of those hydrogens is strong enough to remove that electron from the other. So that means they're going to share them equally. So we have this equal distribution of charge all around that molecule. No opposite charged ends. That's what makes it nonpolar. So if it's polar covalent, you're going to see a uneven sharing of the electrons. You're going to have those oppositely charged ends. If it's nonpolar covalent, they're going to be sharing those electrons equally. So the type of bonds also influences some of the physical and chemical properties of these compounds. So if you're nonpolar, and again, they share those electrons equally, they're usually gases or liquids at room temperature, and they have low melting points and low boiling points. So think about that nonpolar bond. The forces that hold those substances together must not be very strong if it's easy to melt them and it's easy to boil them. Polar substances, on the other hand, have an unequal sharing of electrons. They're usually solids at STP. Remember, that stands for standard, temperature, and pressure. We'll write these down. Standard temperature, and standard temperature equals 0 degrees Celsius, and then standard pressure is 1 atmosphere. So at standard temperature and pressure, they're going to be solid, and they're going to have higher melting points and higher boiling points than their nonpolar counterparts there. So when we talk about the forces that are holding substances together, we're going to look at two different types. We have something called intramolecular forces versus intermolecular forces. They sound the same, but they're very, very different. And when we talk about intra, that prefix intra means within or inside. And the prefix inter means between. So if we're looking for the intramolecular forces, we're looking at forces inside the molecule that hold it together. And so intramolecular forces are bonds. We can have an ionic bond, you can have covalent bonds, and you can also have metallic bonds. So intramolecular forces, forces of attraction within a compound that holds it together. So that would be, if we're talking about the intramolecular forces of the water molecule, this is a bond, that's a covalent bond. That's a covalent bond. This bond holds hydrogen onto oxygen, holds this hydrogen onto oxygen. It's inside the molecule, holding it together as a molecule. Versus the intermolecular forces, the forces between two molecules. All right, so between two molecules. So if we're talking about one water molecule next to another water molecule, what force of attraction holds this together as a liquid, or what holds it together as a solid? So intermolecular forces are the attractive forces between two or more particles that hold them together as a substance, and there's 3 of them. First one is called dispersion forces, and you also see it called London dispersion forces or London forces, named for Fritz London, who developed this idea about these forces. And dipole-dipole forces and hydrogen bonding. So we have three types of intramolecular force, and we have three types of intermolecular force. Let's look at the first type of force, and that's called a dispersion force. And we see these dispersion forces in substances such as the diatomic gases. And so remember, what type of bond holds those together? And if you remember, since they are both the same type of element as you go H2O to F2, that difference in electronegativity, or the ability to pull an electron away from one or the other, is zero. So neither one of those atoms has enough power to remove an electron from another, so they're going to share them equally. So if it's shared equally, that's got to be a nonpolar covalent bond. So what is the physical state? Is it a solid, liquid, gas, or is it AQ? Of all the Hofbrinkel, with the exception of bromine. And we'll see that at STP, that standard temperature and pressure, these guys exist as gases. So if they're all gases, is it possible to take something like oxygen or nitrogen and turn it into a liquid or a solid? Yes, you know that's true. We've seen the trucks on the freeway carrying liquid oxygen. Also, you've seen demonstrations with liquid nitrogen. I think some ice cream places use it to freeze things very, very quickly. So how is it that something that's gaseous at STP can be turned into a liquid or a solid? So remember, we talked about the kinetic molecular theory of gases. Gases are very spaced very far apart. They have a lot of kinetic energy. They're constantly moving and colliding. So how can we get it to go into a liquid, a closely packed substance that has a lower amount of kinetic energy? So you have to do two things. Since we know that gases are very far apart, we would have to compress them. And remember that a sample of gas is mostly empty space, so the distance between those particles is much, much greater than the size of the particle itself. So if we could move them together in one spot and then also slow them down. So remember, the speed is the kinetic energy. The higher the kinetic energy, the faster they move, the higher the temperature. So we would have to compress them, and then we would also have to decrease the temperature. So once we do that, we get them really close together and we get them moving really, really slow. This force, this dispersion force, can kick in, and that's what's going to hold them together as a liquid. So when we talk about these dispersion forces, these are the weakest of all the IMF that we're going to be looking at. And they're defined as being weak forces that result from a temporary shift of electrons in a charge cloud. So if we're looking at this example 1 here, this represents some kind of a diatomic molecule. Could be hydrogen, oxygen, or whatever. And we could see that they are the same size. They're sharing their electrons equally. So there is no reason for these guys to be attracted to each other. If anything, they're going to be repelled by each other because they're looking at this negative charge cloud all around the molecule. But the dispersion force, we have this little temporary shift in the electrons. And we'll come back to this slide, but I want to talk about that Heisenberg's uncertainty principle that we looked at last semester when we were talking about atomic theory. So the Heisenberg's uncertainty principle says, remember, it's impossible to know the exact location and momentum of an electron at the same time. All we know are areas of high and low probability. So we assume that those electrons are going to be, if in this example with the hydrogen, the 2 hydrogen atoms, we assume that they're going to be shared equally all the time. But it's possible that both those electrons can be on one side of that molecule at a time. Or it could be on the other side of the molecule at one time. And when that happens, just like with a polar molecule, since we have both electrons on one side, that's going to make the molecule feel a little bit negative just for a shining brief instant on one side and a little bit positive on the other side. Or in this case, it's going to be a little bit negative on one side and a little bit positive on that side. So it's possible that that can happen. It's just not probable. Everything about those diatomic molecules say there's no reason for one of those atoms to have more control over the electron than the other because they're the same. It's kind of like having a tug of war with a equally matched partner. You can pull and pull equal and opposite directions, and that rope is not going to move. Same thing with those electrons. So when we get that temporary shift here at number 2, this molecule has both those electrons on one side for just an instant, and this molecule on the right has its electrons shared equally. So what happens then is if this molecule here at number 2 has its electrons moved to the left, it's going to be more negative on that side and more positive on this side. So when it comes into contact or close contact with another molecule that in this case is kind of neutral, this positive charge is going to call out to the electrons in this guy. And it's going to pull those electrons over to this side of the molecule. So we end up with, it looks like a, what we're going to call a dipole, a polar molecule, but it's not. We end up with this positive-negative attraction between these two non-polar covalent particles. So this shift in the charge cloud happens all the time, shifting back and forth, but the gases that we breathe are not turning into liquids because we have to have those two other factors in place. They have to be compressed and they have to be cooled way, way, way down because these guys have to be real close together, and they also have to be moving very, very slowly in order for this intermolecular force of attraction to kick in. So it is possible for both bonding electrons to be at one atom at the same time, and this causes a temporary dipole. Okay, so temporary. And it's temporary because it's going to, as soon as we increase the temperature or decrease the pressure, that liquid nitrogen or that liquid oxygen will immediately turn back into a gas. So it just takes one of these molecules in a sample of gas to form that temporary dipole, and then they all will form it. So it's kind of like a domino effect. But it has to be conditions of high pressure and very, very low temperature. This has to happen, and this will induce all the other ones to form those temporary dipoles as well. So temporary because it's not a permanent dipole like water. Temporary because normally they share their electrons equally. So what happens when a temporary dipole meets up with another? It's going to induce, and when you induce something, you force something, it's going to force the other molecule to shift its electron charge cloud as well. So it depends on which end of that temporary dipole comes into contact with another neutral particle will cause either the electrons to be attracted or repelled. So in this case, we have the positive end causing the electrons to be attracted to it. Remember, opposite charges attract, like charges repel. And so now they are going to be kind of stuck together by this temporary dipole, which is our dispersion force. Very, very weak. It's really easy to break those. Just again, increase the temperature or decrease the pressure, and they will go right back to being a gas. So again, under the right conditions of low temperature, really low temperature, and high pressure, one temporary dipole can cause a sample of gas to become a liquid. So think about that liquid nitrogen. They have to keep it in a canister. It's really, really, really cold. You don't want it to come in contact with your skin. It'll freeze anything it touches instantly. But once you open up that canister, you can see that fog coming out. So as soon as you increase the temperature, it turns right back into a gas. The next force are dipole-dipole forces. And these are really strong. these are the force of attraction between two polar molecules, and polar molecules are called permanent dipoles because they are always polar. And so this is a water molecule, and we looked at that example before. Hydrogen is always less electronegative than oxygen, and hydrogen is always going to kind of lose its electrons to the oxygen side. So oxygen's going to command those electrons more, not completely. They do go home and visit their atoms once in a while, but most of the time they're over at the oxygen's side. And as a result of that, that oxygen has that partial negative charge, and each one of those hydrogens feels a little bit positive. And it's always that way. Never changes. It's not a temporary shift, it's a permanent shift, and that's why these are called permanent dipoles. And so we'll always see that with polar molecules. So these dipole-dipole attractive forces are stronger than the dispersion forces, and it explains why water is a liquid at room temperature and why water doesn't fly off as a gas when you open up the tap on your faucet. And again, it has to do with those oppositely charged ends, which gives it that polar name. So the oxygen end feels a little negative, and each hydrogen end feels a little positive. So when one water molecule meets up with another, they align themselves so that those oppositely charged ends are near each other. Because remember, opposite charges attract, like charges repel. And so we have billions and billions of these water molecules lining themselves up so that their opposite charged ends are near each other, and that holds them together, can hold them together as a liquid. And the last intermolecular force is a hydrogen bond, and these are the strongest. And so it's another type of dipole-dipole attraction. So if we were talking about hydrogen bonding and saying what kind was it, you could say it's a dipole-dipole. It occurs when you have hydrogen, of course, that's why it's called hydrogen bonding, but hydrogen has to be attached to or bound to a small, highly electronegative atom that has at least one unshared electron pair. So the atoms that we're going to look at that can hydrogen bond are fluorine, oxygen, and nitrogen. Hydrogen has to be bound to one of those in order to hydrogen bond. So if we look at the electron dot notation of each one of those, and we know that oxygen is in group 16, and it has 6 valence electrons. We know that nitrogen is in group 15, and it has 5 valence electrons. And fluorine is in group 17, and it has 7 valence electrons. So what we're looking for are these unshared electron pairs. So that means the guys that are paired up, those are unshared. Those will not be involved in a bond. So hydrogen has to be attached to one of these atoms. So we can see hydrogen with the oxygen and water. We could see the hydrogen on the nitrogen and ammonia. We could see the hydrogen with the fluorine and hydrofluoric acid. So these are the only atoms that we can see that hydrogen's bound to that can form a hydrogen bond with another molecule. So remember, inter versus intra. This hydrogen here is bound to this oxygen. That's a covalent bond. That's not a hydrogen bond. It has to be between. So when we see a hydrogen forming an attractive force between two molecules. So that hydrogen, remember, kind of loses its electrons to its center atom there, and so it always feels a little bit positive because its electrons are on the other atom. So they're going around feeling a little bit positive. So if we were to have, if we were to have one water molecule coming up close to another water molecule, we know that they are attracted to each other through that dipole-dipole attractive force, but something else can happen. This hydrogen sees that unshared electron pair. So remember, the hydrogen's positive, and these unshared electron pair are negative. So it sees that and is attracted to it and can form that little bond. And this hydrogen's going to do the same thing. So in a sample of water, liquid water at room temperature, the hydrogen bonds are forming and breaking as these water molecules move past each other. So remember, liquids have vibratory motion on movable points. So one's moving past the other, hydrogen bond forms, hydrogen bond breaks, but that dipole-dipole attractive force is always there. So something interesting about this hydrogen bond, if we can get it to form and not break, that's what causes the water to go from a liquid to a solid. So if you watch this video, it gives you a good idea of how these water molecules kind of move around and align themselves so that those oppositely charged ends are next to each other to hold it together as a liquid. And it also will show you how if that liquid is cooled down enough, so the temperature lowers, the water molecules start to move more slowly, that hydrogen bond can form and not break. And that's what forms that crystal lattice. So the hydrogen bonding takes up a little more room, and as a result, that water, when it freezes, gets bigger. The crystal lattice kind of spreads apart and it takes up more space. So this is why water expands when it's freezing or frozen. If you ever take a soda and you're going to put it in the freezer for just 20 minutes and you're going to come back and get it because it'll be nice and cold, and then you forget about it. When you come back later or you hear your mom yell, it's because the can of soda has burst in the freezer because the soda is mostly water, and as the water freezes, that hydrogen bonding pushes those molecules away from each other and it takes up more space. That's why ice also floats on water and doesn't sink. So water, liquid and solid water, is the only solid-liquid duo that this happens with. All other solids are more dense than their liquids in any other substance. So water is kind of special due to that hydrogen bonding. So see if you remember, what are the three intermolecular forces? Remember, there's a difference between inter and intra. And then, which of these are intramolecular forces? It says circle, but go ahead and write it down in your note-taking guide. Hydrogen bonding, is it inter or intra? Covalent, ionic, dipole-dipole, metallic bonding, and dispersion. So now we're going to go into properties of liquids. And liquids, we know, have the a definition of having a definite volume but not a definite shape. We know that liquids have vibratory motion on movable points. So the one liquid molecule can roll around another liquid molecule. And they're closely packed, but they still can move. And so that's why they have that definite volume. They have enough attractive force to hold them together as a liquid, but they have enough kinetic energy that they can change position and they don't stay together as a solid. So the kinetic molecular theory tells us that liquids have no definite shape, but they do have a definite volume. And it has to do with the amount of kinetic energy that a liquid possesses. So that liquids have more kinetic energy than do solids. Liquids have vibratory motion on those movable points. So they are still closely packed to really close neighbors, but they're able to move around each other. So that's what gives the liquid the ability to flow. So when we talk about density then, what would have a greater density? Remember, density is mass over volume. Would it be a liquid or would it be a gas, and why? So we know that liquids are going to have the greater density because, remember, mass over volume. Since liquids can be closely packed, their volume is going to be a lot smaller. Remember, gases will take the volume of their container. Liquids have a definite volume. So if we were to look at the density between water and its water vapor, liquid water is 1,250 times more dense than the vapor. So remember, the water vapor, you get from liquid water to water vapor by adding energy. And so once it turns into a vapor, it's in that gaseous state, and the particles move far apart from each other and have a lot more kinetic energy. So So think about the difference. Liquids are very dense. Its gas counterpart or its vapor counterpart is not dense. So what's holding the particles of a liquid together that's not holding the gases together? So think about water and water vapor. So why does water stick together as a liquid, but it's vapor, it's going to be a gas? Well, it's the intermolecular forces. So if we're thinking about water, we have dispersion forces, we have dipole-dipole forces, and we have hydrogen bondings, all holding water together as a liquid. Once we add enough kinetic energy that we can overcome those IMF, then that goes from a liquid to a vapor or a liquid to a gas. So when we talk about fluids, a fluid can be a liquid or a gas. It's not just a liquid. And fluidity measures the ability of a substance to flow. So remember, you have to be able to move around each other. You have to be able to diffuse in order to flow. So gases can diffuse a lot or flow a lot more easily through each other than can liquids. Because remember, the particles of a gas are very, very far apart, and the shortest distance between 2 points is a straight line. So they can get to where they're going much faster than a liquid can, which has to move around the other particles. So the more IMF a substance has, the less fluid it's going to be. So if we look at this illustration going from a gas back to its liquid, back to its solid, if this were water, right now we have no IMF. There's nothing to hold that together. The kinetic energy is really high. There's no forces of attraction that are going to hold it together. If we cool that substance down, we can get it to turn into a liquid. And so now we've got the hydrogen bonding. We have the dipole-dipole attractive forces that are now holding that water vapor now as a liquid. If we can cool it down even further, then we're going to have that hydrogen bonding kick in and form and not break, and that's going to hold that together as a solid. So the more IMF a substance has, the less fluid it's going to be. So we're going to look at the resistance to flow, and that's called viscosity. So thick liquids, we usually say, have high viscosity or are viscous. So we have three things that can influence your resistance to flow. The first one is the type of IMF. So the more IMF you have, the less fluid you will be, the more viscous you'll be. So remember, we're resisting flow. So lots of IMF holds you together, doesn't let you flow, and that would be a factor that affects your viscosity. The second one is the size of the molecules. So think about large molecules having a lot of drag. It would kind of be like if you're trying to pass through a crowd of people, maybe going through the quad at lunchtime, and you decide you're going to stick your arms out and keep them straight out from you as you're walking. It's going to be harder for you to pass through, plus you're going to annoy a lot of people because you have a lot of drag. Versus when you pull your arms in, then you can squeeze by faster. So the bigger you are as a molecule, the more difficult it is for you to flow, the greater your viscosity. And the last thing is the temperature. So remember, temperature is a measurement of the average kinetic energy. If you have a high temperature, that means your particles are able to move faster, which means they're going to flow better. If you have a low temperature, your particles are moving slower, which means they are not going to flow as well. So you can kind of see that with pancake syrup, Mrs. Butterworth. At room temperature, Mrs. Butterworth, the liquid is thick. And it's thick for two reasons. It is made of sugar, and the sugar molecule is very, very large. And at room temperature, the kinetic energy is kind of slow. So if we take Mrs. Butterworth and we stick her in the microwave for a couple minutes, then you're going to find that the syrup is runny. And the size of the molecules haven't changed. It's still sugar, but now the kinetic energy is higher, and so those particles are able to flow past each other with more ease. So let's look at the factors that could cause an increase in viscosity. So think about these. If you decrease temperature, does that increase viscosity? Yes. Decreasing molecular size? No. Decreasing the amount of IMF? Yes. Increasing temperature? No. Increasing molecular size? Yes. Increasing the amount of IMF? Yes. So those are the factors that would cause an increase in viscosity. So now we're going to talk about surface tension, which is a property of liquids and something that you see all the time but maybe don't quite understand what's going on. But before we talk about surface tension, I want to talk about forces. And a force is defined as a push or a pull one object exerts on another. So push or pull, one object exerts on another. So when we talk about pressure and the pressure of a gas, so pressure is equal to force over the unit area, and a force is a push or a pull. So we're talking about gas pressure. Remember how gas particles move? They are hitting the sides of their container, they're hitting each other, constantly moving and bouncing around. Are they pushing or are they pulling? So think about that. Gas particles, one runs into the other. It's not pulling it towards itself, it's pushing it away. So gases push. Now let's talk about IMF, the types of IMF that hold water together as a liquid, or any IMF, intermolecular forces. That's the attractive force that holds things together. So when we talk about intermolecular forces, that's going to be a pull. So now we have two different types of forces here. And if we look at these, the first example with these two gentlemen, and we assume that they are of equal strength, equal mass, and they are pulling back on that rope with equal and opposite force. So remember those vector arrows. I'm going to show them equal and opposite. So if it's equal and opposite, who's going to win? Well, no one will win because there's no reason for that one person to win over the other if they're both equal and opposite. When we have equal and opposite force like this, it's called balanced. And you always have acceleration or movement towards the greater force. If the force is balanced, we don't have any motion. So they'll stand there forever pulling on that rope and nothing's ever going to happen. Now in this second example, we have more people on one side of the rope, and we're going to look at the force now. So we have this guy pulling back with this much force, and these guys pulling with this much force. Remember, you're going to have acceleration in the direction of the greater force. So the rope is going to move this way. And this is called a net force. So with a net force, you have acceleration or you have motion in the direction of the greater force. With a balanced force, you don't. So when we talk about surface tension, and it's like when you see a drop of water on the surface of your car or the surface or something, that water has a tendency to form a bead. The water doesn't spread out flat. It kind of holds itself together, and that's due to surface tension. So let's look at what's happening. If we are looking at, and we can go, submicroscopic, and we're looking beneath the surface of this liquid, we've got water molecules that are at the surface and under the surface. And let's talk about the force, the IMF that is holding these water molecules together as a liquid. We've got our dipole-dipole attractive force, and we have hydrogen bonding. So this water molecule here, we'll color him red, he has the force of attraction to the water molecule that's on his left and the water molecule that's on his right. He's got a force of attraction by the water molecules on top, the water molecules on the bottom, and he also has an equal force of attraction water molecules behind him and in front of him. So in all directions, he is being pulled with a balanced force. So remember, you have no acceleration in the direction if there's a balanced force. Everything you stay put. So he's not responding to any of those other forces by moving towards a water molecule due to a force. He is moving around because the kinetic energy is high enough, and he's moving around from place to place because he's got that vibratory motion on those movable points. But he's not moving around due to a difference in force. Now, let's say we'll look at that same guy, and let's say he makes his way to the surface of the water. Okay, so now he's at the top, and let's look at the types of forces he has. He's experiencing a force of attraction from the guy on his left, from the guy on his right, the guy in front of him, the guy in back, the guy below him, but we're missing a force. Which force are we missing? The one up here. There's nobody up there. So now we have a net force. So we have a force in the direction that has the greater force, so that we're going to have acceleration in the direction of the greater force. So left and right is equal, front and back is equal, down is not balanced by up. So now that means every water molecule at the surface of the water is constantly being pulled inward or down. So that's what gives water that kind of like skin, that surface tension when you see it as a droplet, or if you've ever put drops of water on a penny, you can see that you can really put a lot of drops of water on there because the water molecules are constantly pulling the outside water molecules inward. And that's what surface tension is. So surface tension is the effect that the inward pull of particles in the interior of the liquid have on the particles on the surface of the liquid. So they're constantly being pulled inward, and that's what gives it that tension, that surface. Here's a video for you to watch. I'll clip it into your note-taking guide. It's this lizard that can run on water, partially due to surface tension and partially due to kind of the water displacement because his feet are kind of big. Okay, so hopefully you have a good understanding of that. We're going to stop there. I think in your note-taking guide it goes on about a little bit of soap chemistry and capillary action. Don't worry about that. But I do want you to summarize what you learned by using at least 5 sentences.